Good evening. Welcome to today's Sliver lecture. What I always forget to mention, what you might know from the posters, that the program is about digital craft. And I guess today we have somebody who is really embodying what you might call digital craft or digital craftsman. We have Cristiano Ceccato, and Cristiano is an architect and a computer scientist. So maybe architecture stands for crafts or for application, and computer science is what the digital is all about. And I think we are going to have a very interesting talk about how these two things interlock, or how these two things work with each other. He got his architecture diploma from the Architectural Association and an MSc in computer science from the Imperial College in London. This is close to the Victorian Albert. And he's a fellow of the World Society of Arts. I read a few things because I might mix up terms. For 7 years he has been, or he worked in the offices of Frank Gehry, where he was responsible for the development and application of parametric design tools, integrated modeling principles, and associated digital construction methods. So you see all the way from software to application in the material world. At Gehry, he was Director of Research and Consulting, and through Gehry Technologies, which was a digital project program that I do remember when it came, and we had a studio in the architecture department that was expressly trying to bring Gehry Technologies or the software to the studio. That many architects thought that this was maybe one moment where they could regain what they had lost during the 20th century as power to people from supporting sciences. The thing was that with Gehry Technology, and the architect could go back into the central role of orchestrating the whole architecture project with everything that is related as science. At the moment, Cristiano is associate at Soho Architects in London, and his professional focus is on technical team management, systems and cladding, which includes geometrical and structural rationalization, and constructability resolution of structural and envelope systems, and he's also very much involved in cost control. So it is rare that I have read a profile that was so complete. Thank you very much for coming. Welcome.
Schönen Dank. Ich hatte mit Ben Ceccato besprochen, ob wir die Vorlesung auf Deutsch oder auf Englisch halten. Ben just asked me to speak in English, so I will do so. If you want me to repeat things in German, then please do. Thank you, Rainer, for the very nice introduction. I'm very pleased to be here. I think even more than me, Ben is pleased to be here because he's been chasing me for 9 months. And he gets me here every time we had a day. It was like, oh no, I have to do something else. So anyway, I'm glad to finally be here on such a warm day, and I know you're all getting diplomas, so you probably have a lot of better things to do than to listen to me. One of the things I wanted to point out, in the interest of time, what I've done is I pulled out a couple of ongoing projects that I can share with you just to give you a flair of some of the kind of work that's going on. And kept sort of, shall we say, the theory side a bit more to a minimum, because I'm sure you hear a lot of more qualified people talk about those things than I do. So there's an aspect of how a lot of this stuff gets translated from research and kind of computational know-how applied to the process we're making and making things and putting them together within a And that professional context, in the case of not just our practice, but increasingly in many practices, is now global. So we have to now look at operating in many, many different environments from a professional standpoint, different construction industries, different types of projects, and clients have wildly different ideas about what it takes to get a project designed and get it built. So, and maintain the level of quality that's required sort of across the board. And part of that, which I mentioned, I do many, many things, including managing projects and working with various teams, but also a big part of that is also developing the work, which means actually being able to talk to prospective clients and find the right people that you can work with who are willing to try to do a certain kind of project with you. And that's quite a difficult thing to do because many people have a lot of interest in the kind of work that the office does. But then when you start really going into what it takes to get something done, it becomes a very, very intense dialogue. So looking at the kind of complete life cycle, if you like, of a building project, which starts really at how do you develop a business, how do you start working with clients, how do you look at the work and some of the research themes that exist in the firm, and how you then apply them when it comes built. So just a little bit about the office, which I'm sure you all know from Zaha's studio, and when Zaha and Patrick come to Vienna. The office is operating globally now. We're headquartered in London. We have many people from many, many countries. We have many, many graduates from the Angewandte working with us. In fact, I'm working with one of them on our first project in New York with Hannes Schaffelner, who some of you guys know. And we're together getting this project built with the whole team there. So it's actually nice to come here because I heard so much about the school from Hannes, and that's the first time I've come again. I've been to the end. So therefore, I'm going to quickly go over a couple of projects here. One of them is this one in New York, which is the related West 28th Street, and use these projects as a way to kind of describe a little bit the paradigm shifts and the thinking that is going on in the office. As you know, the office was founded in the late 70s by Zaha. It's grown, particularly also Patrick's presence. But most importantly, now that there's a lot of work that needs to be designed and delivered and built, we've had to address a lot of issues about what are the best ways to get this done and how to map it to different areas around the world. So these kinds of paradigm shifts of how you work are fundamental because it means on one hand taking chances, and it means also being responsible for what you're trying to do. In previous life, I did some cross-disciplinary research with Boeing when we were in California. And one of the interesting things was that Boeing was using a lot of the same technology that we were using in Frank Gehry's office to design aircraft. We were using it to design buildings. And so we developed this kind of dialogue with Boeing where we were like, we'll show you ours if you show us yours. And they're making airplanes, they're making buildings, there's no real conflict of interest, but there was a really interesting richness into this process of making and the control of the making process and what you have to do to get it done. And if you look back at the history of Boeing, it actually mirrors kind of what's going on in the construction history today. Namely that when Boeing, when Juan Trippe, who was the chairman of Pan American, approached Boeing in the 1960s, said they need a much bigger plane. And Boeing said, well, we can build this. They didn't have the facilities to do so. They quite literally bet the farm. And for those of you who've been to Boeing in Everett, Washington, when they built a new factory, they basically came this close to bankrupting the entire firm, to making a paradigm shift, to making a quantum leap, to being able to build the biggest plane in the world. They had to build the biggest building in the world, which is the Everett factory. And what goes on there is very interesting because with the evolution of time, Boeing's kind of gone forward from a very, shall we say, manual and laborious process of putting aircraft together to documenting them in what's called a virtual mock-up. So basically building the aircraft virtually before it actually ever flies. And you can test its flight systems, you can test how you're going to assemble it, what is the best production line to put it together. That's something that they started to do and went further and applied parametrics where most companies today, the aircraft industry, won't design a plane, but they'll design a family. So in this case, many of you fly long distance, you know these planes, the 777. They make one 777, they actually can stretch it and reconfigure it depending on the market they need to achieve. But if you think about it, architects are constantly redesigning every building from scratch. There's an ethos about it, there's an ethos about research and finding something new, but there's also something about efficiency here of solving a problem in an effective way. That goes further to decentralization, which is something that we see in our industry today. This is a 787. If you haven't flown on this plane, I hope you can try to do that because it's really quite a remarkable aircraft. And it's actually made now all over the world. So they've actually gone from a centralized design process to decentralized fabrication process, and now to actually decentralized manufacturing process. So everything is being taken apart and then needs to be transported as little components to a single job site in the state of Washington, where it gets built. And so the interesting thing about that is they had to make the airplane to make the airplane. So they invented this modified version of the 747 called the V-Lifter, which was in itself a kind of a new aircraft. And this is used to carry all these pieces of aircraft, the 787, to this factory. So now you have the aircraft that makes the aircraft that's made somewhere else, right? So it's gone away from that kind of manual labor to really a digital kind of controlled process where you can actually simulate the factory and really control the process of the making in a much, much more dynamic way. And this is something, again, that you can go visit when you go to Seattle. And you can see actually how that comes together as a kind of the nucleus of really what's become a globalized process. So there's some interesting analogies to be derived from that. One is, and this is there's only two boring slides like this, and then it's going to be much more visual, so bear with me. The 2 minutes that I can give for me. One is basically how a company like this has controlled risk. In their case, risk is risk of being able to achieve a project like this and getting it built by minimizing the amount of parts you have, by increasing the amount of management that's required, and basically managing the proprietary knowledge. So basically, from plane to plane to plane, you have an increasingly decentralized process, but that's actually based on knowledge management. So what you're doing is teamwork, right? So you're working with global teams where every subcontractor is taking responsibility for fulfilling one part of this airplane. That means you really bring the best to bear in a project, rather than Boeing being one big company and doing everything themselves. They now leverage the very best of companies around the world, but can spread the risk. So if you compare this to construction and design, something very similar has happened, albeit probably something like several years onwards with a much more stretched time frame. If you go from, you can say, look, curvy architecture, blobby architecture has been done for a long time. If you look at the work with Aero, Saturn, or even what Gary did, and to the work that we did recently, for example, the Galaxy Soho, there I'll come to it in a few minutes in a bit more detail. But again, there's a similar process going on, where we're looking at basically reducing the risk. In this case, it's the risk of the project not being built well. It's the risk of the client not being able to achieve the commercial needs he needs to do. If you're working on a commercial project, such as the one on the top right, the Galaxy there. And at the same time, leveraging an increased amount of knowledge management and team management, and ideally also a process underneath it, which is this kind of integrated digital design process that Rainer mentioned, which is really bringing to the fore how technology, it's not really about a tool like, my IT is better than something else or Revit. It's really about process. It's really about how people ultimately, the human dimension, work together to achieve a more complex project in less amount of time with a lower amount of risk in potentially an unknown situation like a new country. Like if we start working in a country we've never worked in before, Brazil or name a country, we have to understand what can the construction industry of that country do. And if we design something, could it get built within the framework and the risk parameters of what that country needs for us? So it takes a little bit of thinking about that. I just want you to bear this kind of diagram in the back of your mind as I show you a little bit of the work. So before we get to sort of some of this New York stuff, it's interesting to note that the office doesn't do research, as I'm sure you know from Zaha's teaching going on here with Zaha and Patrick. And a lot of that has to do with kind of this idea of looking at not one solution, but families of solutions that through technology can be modified and can be replicated and diversified into a series of different design solutions that can perhaps be a better, more effective or less effective fit for a particular design problem. And the office has a lot of dexterity in working in this way, and that allows us to explore design solutions very, very quickly. And this isn't done just in a kind of a formalistic way, but there's a lot of knowledge that gets embedded in these models and these digital constructs to really be able to inform a project such as this one. This was for a project that didn't get executed in New York. But the idea here was to convey different options to the client. The client had different ideas about what they wanted to do. Much of this was driven by New York construction requirements. There was an existing building on site. There were requirements of retaining certain percentages of the building and building on top of it, or to try and work with the client to see if the city of New York would change its laws and allow it to completely demolish the existing building. So there was a speculative aspect of what could the client do and how much could that push the design further. And so when you work with a client like this, you're looking for a solution that you know is going to have an aspect of being achieved, and an aspect maybe that if things were changed, you need the framework. So the building on the left is playing within an existing framework that works. In a playing field, you know, tonight the World Cup of football starts, right? Brazil against Croatia. And they're playing within a field, but if you stretch that field, maybe you can do something different. And that's what the tower on the left does. It assumes certain legal statutes have been changed in the city of New York, and we can do something different. So that actually was a competition that Hannes Schaffelner and I worked on, Hannes being a graduate of this place. And a few months later, we started working on this project, which is now actually getting built. We just needed a hole in New York for the foundations, which is on the High Line. So if you know, if you're familiar with New York, there's the High Line project, which is this elevated walkway. And this is on the corner of the High Line and 28th Street, so we're basically looking west here. And this project is basically a residential project. It's not a very big project, but it's a very, very interesting project because of its scale. And it's also interesting, as you'll see, because of the mix of the units, and basically that the morphology of the project is the result of working with the city laws of New York. So as if any of you have ever worked with New York or worked on U.S. projects, you'll know that there are many, like many other cities, of course. There are many zoning rules, right? So in this case, you have many different zoning codes and construction codes, and they sort of almost dictate what the shape of the mass of the building is going to have to be. And if you want to get the project done in a relatively expeditious manner, you have to work within those confines. If you want to step outside them, then the client has to go to the city of New York, you have to get code acceptance, you have to do all kinds of different things. They have to buy air rights, they have to do many different things which will delay the project, and therefore delay how quickly the project can come to market. In this case, the apartment's being sold. So it makes for an interesting design exercise because you have a set of rule framework that you have to work with. In this case, you'll see, I don't really have a pointer here, but maybe I can use my mouse. There. You'll see basically that there's a step here. So it's a little bit of a step over here, right? And what's happening actually is that there's one of those things you see, you know, there's kind of a setback. The building is higher, it gets smaller, so that's more light into the streets. And so what we did is, in order to, maybe I can actually do it with this one. In order to, this work? I think so. To fit within this boundary here, see that? Isn't that cool? Actually have a lot of undulations going on here, where these balconies are going in and out. And by doing that, when you actually get to the real step above, which is here, you're not so aware of the step. So you've done a kind of an architectural massing trick to sort of go away from that typical kind of wall. You can see, for example, over here, some existing building. You can see that step over here. That step is not very nice. And by doing this trick, we can erode that. We can make it a much more porous building, while at the same time offering these kind of balconies to the people who live in here. The other thing is that there was a very broad range of things that the client kept on exploring in terms of what kind of units are these. These are units for sale. There's only 41 of them at present. That might change again, but I doubt it. And so one idea that Zaha had actually was to look at this idea of the scissor section, which is basically not have all the units on the same floor, but you're shifting them by half the floor, right? You'll see that on the right, which are the pink units, and the orange ones. Let's see if I can show you that right here. Basically, you have a half step, and what the half step does, it allows you to separate the units into different mixes, but it also creates a sense of exclusivity person who's going to buy it. So instead of thinking I'm living in a big block of units, like I'm just another apartment, like Wohnungsblock. I'm actually living in a more special zone because my neighbor is really a neighbor. He's like a half neighbor, right? And so the question is how you do it. Well, so what Hannes and the team came up with this idea of this weave. And the weave here is basically what we call a chevron, which are these big spikes that move in and out. What they do is that they cover the transition in these half floors. So as you'll see, the construction aspect of it is relatively simple, but there's some architectural tricks here that are working towards increasing the value of the project to the client. The other thing that's really nice about this is the multiple layers of perception of this job. Because you can see it from the High Line, which is a very public way. There's some people who are going to have people looking into it. And then there's this kind of more secluded view, which is from the street level. This is on 28th Street looking west. And you can see that you see a very, very different image of it. You see a different perception of it. And that's something that's really nice to see in New York, because New York is such a 3D city in a way. To be able to publicly be able to look at the building from the public streetscape on two different levels is quite rare. Right, so here we're looking towards the north, and here we are looking a little bit closer now into these units. Again, you see this kind of chevron split. And then you see the apartments here. They're actually they're very beautiful, very spacious. They're very large apartments, and each one, by having this unique morphology, the weaving in and out of the steps, become a very, very unique apartment. You're not buying just one flat building; it's your own special shape. Some of these on the top, this is an older image, but this is kind of principle where they have their own roof terrace, which is again quite rare in New York. And on a nice day like this, you can sit outside and get a tan. So the building itself is actually structurally not very complex. You have a concrete frame system, which is basically has this split levels, like two buildings tied together by a common core, and then there's a secondary core to address the back of the building. And then you have these round bits that you see where these curved balconies are. Their appliques are basically bolted on, pre-constructed and bolted on. What then happens is you close the building by adding glass. This was the original proposal, which was essentially looking at putting the glass on the floor to ceiling level. It's evolved since a little bit. It's become a little bit more of a curved wall, which means that it floats in front of the slab edge. But essentially the idea is that the building is essentially closed with the glazing. And what happens is, when you add these bands, what the bands do is, you can see there, you can still see the vertical split, and then you can see that there are the glazing is dark blue. The light blue is essentially, they're essentially spandrel panels that are blind panels that basically then get covered with this folded metal. And so the folded metal is an applique on the front, which is basically your aim screen. What's interesting about that, which was something that we really pushed on this project, was the idea of developing as a kit of parts. So it's like a Lego, right? So you actually can see that, again, there's many special variants of this in the end result. The original premise was, it's going to be a kit of parts that I can apply in different conditions. And if I can solve those conditions, I've basically solved the whole building. And that's interesting because you're looking at a parametric idea from a different point of view, that rather than saying it's about deforming a shape, in this case it's about reconfiguration of components to get a lot of movement in there. Right, so these are other views again, just of these kinds of kits of parts. And this gives you a little bit of an idea of what's going on. This is again an older version of the detailing, but it's essentially the same idea where you've got basically you're closing out the building, and then you're applying what is essentially it's about this big, and it's a stainless steel continuous pipe built out of components. And all of this obviously gets developed on the computer. The computer helps us continuously to revise this as we're designing the external part of the building, the shell and core. The unit mix is changing. The layout of the building is changing. We want more units, we want less units. And that happens because the client is working with their marketing team and with their research team on the business side to figure out what's going to be the optimal configuration for going to market in the city of New York. So you need a flexible process to be able to cater to this, and at the same time crank out the kind of drawings that you still require. We're not going to, we don't live, unfortunately, yet, let's say, where you don't need paper drawings anymore. That'll probably come. If you work in countries like Singapore or Australia, on public projects you now have to submit by law a BIM model, at least a simple IFC BIM model. But in New York, we're not really there yet. So there's a combination of kind of paper-based information that many people understand and models. And the favorite model that went around is this one. This model is about this big. It's the kind of model you guys can't see it. It's this big, it's this big. It's just a piece of cardboard. And I guess it showed, Hannes studied here, so he made this. And this piece of very thin card, which shows the weaving, we would go to the boardroom on 60th Columbus Circle, 60 Columbus Circle, which is the headquarters of Related. It's a very big property developer, probably the biggest property developer in New York is a client here, related companies. And we're sitting in the boardroom with Steve Ross, who's the owner, and the other top executives, and they're passing this around. And this, the tactile element, in fact, hold this and look at this, and, this helped them understand the project more than any amount of drawings, any amount of 3D computer stuff. Just looking at this model and really getting a sense, okay, this is what you're really trying to do. So sometimes the mnemonic aspect, the tactile aspect of something like this will actually help you get to the goal faster than in rendering. Obviously, this then plays itself back out into the metric system, and then we start having to consider how these individual pieces play out. One of our other people who is leading this team, Alberto Barba, is previously worked on the museum in Michigan State University, the Light Road Museum, and that was a museum that was driven very much by folded sheet metal. And so that kind of knowledge of what's required to do that was very helpful to us. I had just finished working on the Galaxy Soho project, which I'll show you next in Beijing. And so that was also about folded metal plus the gear experience. All of that knowledge comes together to really be able to ascertain how are we going to make this thing so it can really be made. And so you start by making mock-ups. This is a full-scale mock-up. It doesn't look very big in this picture, but it's actually enormous. It's like the size of this room. Very, very big. And basically it's made by a fabricator in Philadelphia who's a contractor. And again, it shows the complexity here because we're talking about our office is in London, the client is in New York, this contractor is in Philadelphia, and the glazing contractor is actually in Italy, in the north, in Bozen, down the road from here. So suddenly you have to bring, in a globalized process, all the information together and get a single piece of information together that everybody can share at the same time. So as we're going forward, now these panels should not be made as a single piece. We're looking at different solutions, different options. This is actually all a work in progress. And what you're seeing here is basically the pink model is the original design, the 10 model by our office, which is this kind of pink layer, and overlaid on top of it is actually the panelized model being done by the contractor. We're looking continuously at what are the deviations, what are the concerns, and this is happening in real time using different software tools, including basically models that live in the cloud, so that we can upload and download these things and everybody can look at them at the same time, and basically begin to develop a strategy that is informed by our own experience, by the goals of the project, both architecturally and programmatically, but most importantly about material performance in this case. It's about what does it take to form and make and assemble pieces that then have to come together with a glazing system, such as the one on the left, and be manufactured at a cost that we have available to us. So this coordination has to happen in this environment. We're not really only going to solve the 3 models and then ultimately be able to then go back and build more mock-ups. That starts with panelization. And the result, of course, is this. This is as professionals what we need. This is the client team. In fact, you can see the tallest guy there with the white shirt. That's actually Hannes Feller himself. We're still looking at mock-ups and making sure that you retain this kind of photograph in your mind if you want to go into practice. You have to be sure that you maintain confidence that what you're doing can be done and that the client believes that you can actually achieve what you set out to do. Moving a little bit more towards the other side of the globe, we're going to talk about another happy lady. This is Zhang Qing. She's one of the owners of Soho, China, which is a very big, it's now the largest independently held property development company. Them and Vanke, I'm not sure quite as the biggest one in China. And this is the Galaxy Soho project, which was the first of what we're now on project number 4 with this company. So we're getting close to about 2 million square meters of construction with this client, which is very good for us. This first project was 330,000 square meters. The second one that we did, 1 Genius 550. Soho, previously called Lincoln, is about the same size. And then we're doing another one that is like about 400,000, 300,000 in Beijing. So we're doing a lot of work with them for about 1.2 million square meters of construction. What's interesting about this diagram is increase in speed. Okay, so what you can see is that there's a compacting going on here. Let me see if I can. Let's run out. So I'm just playing with the. Never mind. But what you see here is these two thin red lines, and they become tighter and tighter. The construction process, you can speed it up to some extent, but what you can really compact is the design process. And you compact the design process by thinking ahead rapidly, how can I develop solutions faster? And so part of this is what happened, again, some analogy to Boeing, but basically looking at design solutions and design optioneering. In this case, these are really just in-house studies of parametric power layouts, where I can make variations to a building and look at them taller, bigger, smaller, wider, look at controlling the cost, controlling the GFA, making sure they're meeting the client parameters, and then putting them to use. So if I start doing much more sculpted massing, say in this case, this was an early research for Soho, one of the projects, you see what the computer started to tell me in real time is that however I modify this form, it is going to tell me what my area cladding is, what my GFA is, and so on. And so, this starts coming to fruition on a real project like this. So this is the Galaxy Soho project. If you know the city of Beijing, we're now looking west. So basically the Forbidden City is here. Right, this is this black thing here, the Forbidden City. And so we're right here on the second main road, and Dean is here, and you know this very well. So you can help explain to people where this is. But basically, you're within the second ring road used to be the historical walls of Beijing, which were demolished in the 1950s. So you're actually inside Dongzheng, which is the eastern part of the actual original fortress city. So you're kind of really in the center of town. It's like being inside the Ringstrasse. It's a very nice location. And again, this building, the client wanted to move forward very quickly, but also had the challenge that it was the first really curvy building that they were doing. So the client builds a lot all over Beijing, and not recently around China. They're actually now starting to build stuff outside of China, but in this case, it was really about a challenge of being able to work on something that's geometrically complex and still maintain the economy, the cost per square meter of construction, and the speed and the quality of delivering this project, just like if they were building a box building. But it's very, very different. One of the challenges also is getting to know your client. So in this case, Soho China, or Chungguo Soho as they're called, has multiple departments within them. And these departments have backlogs, and they work with different teams. So in this case, you've got the design department, budget department, construction department, so on. Our firm, and then BIA is like the local architect, it's called the Design Institute. It's a very large architecture firm that's run by the Chinese. We working for them in the design department. And then there would be another department, which would be the construction department, which would actually be working with China State Construction, which is the main contractor, not the general contractor, because on a contractual basis, China self-performs, so they do not appoint a general contractor, they appoint a main contractor to do construction work, but they actually take construction management in-house, and will do the construction management and the risk management of that in-house. As that, by the way, does related on the New York project. So it's interesting to see that a lot of large clients now, or developers, are doing in-house construction management. And they would then hire different cladding companies. So we found that as a way to kind of overcoming a lot of the complexity of working with so many departments is actually to establish a common platform of information sharing, which, again, was working in this kind of three-coordinated environment, but at the same time would allow you to implement digitally, if you like, the contractual relationships that necessarily are established of managing the project. And what's most important here is kind of this scope and interdependency agreement where basically we're sharing scope that's shifting between between different design phases between ourselves and the local architect. So this kind of basically produces, if you like, the holy grail, if you like. It's got an integrated project delivery process where everything lives in one common 3D environment. This obviously changes from project to project, but essentially that some people call it BIM, but to me BIM is, I really like to use that word because it sounds like you make a model and you finish. And actually it's a process. It's about something that continuously gets revised, updated, fed in with research, gets modified by many different people. So it's a living, breathing thing that cycles through the life cycle of the building. Obviously that happens on many, many different tools. This is kind of a slightly older snapshot, but again, depending what's going on in the firm, the issue of moving data around between different technologies becomes very, very important and a very complex process. So that kind of interoperability of information, you have to make sure that it's non-lossy, that what you want to keep from one software to the other is retained. For us to deal with a lot of curvy geometry, for example, if I make a project in I don't know, Rhino, and in Rhino you've got surfaces that close, you take them into another software like CATIA or IoA, and actually surfaces are not closed. Because the digital tolerances go to different levels behind zero, and more importantly, different software companies write the code for the NURBS algorithm differently. So there's a blur zone now, because my curve might look like that, but I take it somewhere out, more like that. There's tiny variations. So where's the real curve? And so at Frank's office, what we used to do is we used to determine you only work in CATIA or digital projects. If you're looking at the contractual information, it's in one place. And that's what we did on this project as well. We said all the information is going to live in one place, everything else is an interpretation of that. Because otherwise, you're never really sure where you're going. So, again, another nod to Boeing here. Boeing has this really interesting idea where they fabricate directly from their 3D models all the different wing components and structural components. And they refer to that, instead of calling it contractual information, they refer to that as authoritative data, meaning that the data has authority for manufacturing. It's been vetted, and it's been released for manufacturing in countries called authoritative data. So in a way, we developed this idea of parametric authoritative data, where we're saying the parametric model keeps on evolving, as I mentioned on New York. We have different requirements that the client has, but we have a construct of the model put together where we know that the logic of the building is there. That's been squish, squash, threshold. We actually had to increase the size of the building rather than reduce it because the client added more GFA, because in Beijing they're allowed to move GFA. They had multiple projects in Beijing. It's really interesting. And my understanding of it was that they could actually agree with the government to move the GFA from one project to another. So one shrank, the other one got bigger, ours got bigger. But also, if you look at here, these models, there was a design process, and as you go through this design process, these are very simple, again, cardboard models, much like the one I've seen upstairs, to kind of get increasing to the shape. This is on one hand dealing with the size of shape of buildings that the client was looking for as volumes, but also in Beijing now you have very strict laws about casting shadows on your neighbors. So what these canyons also do is allow light channels to pass through to your neighbors, make sure you're not basically completely putting them in darkness. So basically now we are confronted with how do we make this? So this is an original shape that came out of a software called Maya, which I'm sure many of you use here. And you can see that it's a very nice shape, but there's at the moment no real logic about constructability applied to it. So what we have to do in this case is look at building, and in dialogue with the client, establish what are you going to make this building out of? You could make it out of, given that it has this kind of banded look, what are these bands made of? They could be metal, sheet metal, they could be stainless steel, they could be welded plate, they could be FRP, which is fiber reinforced plastic, they could be GRC, they could go visit Wolfgang Lieber, we talked to him, over in Salzburg. What is this made of? And one of the things that tells you what this could be made of is if you look at the Gaussian curvature analysis. So you're looking at the idea of curvature C Gauss, which is in any point on a double curved surface, you have the minimum and maximum radius. You take the inverse of the square root of the sum of the squares. If you like to, that's the math bit for today. And basically you can tell how close you come to single curvature surface within a larger surface. So in other words, the piece of paper, this is why a lot of Frank Gehry's models are made of paper, and I saw people folding paper upstairs, is that a piece of paper is basically a single curve, unless you mold it or make it wet and form it. So what can I achieve? This basically, any form of paper has zero Gaussian curvature, right? Because I can lay it flat without deformation. So basically, I have one curvature radius here, the other is a straight line, which means the radius is infinity, the square root of 1 over that is basically 0. So it tells us that if I can approximate some of these curves within this band, I can probably do it with single curve metal, right? I don't need a mold. And that cuts the cost of manufacturing by like a factor of 5, right? Something like that. So even if you're using flexible mold technology, the speed and the availability of how many subcontractors, remember, we're talking about a project here, when you look at the panelization of this, we have something like 55,000 different panels, right? Not one company is going to be able to do this. You're going to need many, many companies working together. So suddenly, you're looking at what is the lowest common denominator that any one of these metal suppliers in China, because you're not importing anything, there's no money for that, can make. And they can make flat metal. So basically what came out of this is an analysis in conjunction with the client of breaking down the project into its constituent components, where we're looking, we can basically assign a certain cost per square meter to different component types and look at them, how they will be manufactured. So first pass at this is now looking at if I build these as developable surfaces, so I'm approximating the curve. So these are now single curved, they're not double curved. Obviously that green shape is curving in 2 directions, but we're so close because of the Gaussian percentage of it that I can make a single curve. And the trick is, you have to look at this as I keep showing you this project, is this curve. Perception to the human eye, even though there's straight segments, it actually continues to look like one continuous curve. And that's really, really important because in the end, that's what you want to achieve, is a sense of curving in plate as well as curving in plan. And the fact we have these slots for the windows allows us to make those tiny bridges. One aspect here, working with our team, was that if you lay these panels flat, right, so you take, this is not a projection, this is basically unfolding these bands. So if I take my belt off, I can lay it flat. And you can see here, these are all now flat, so I can make it out of flat metal, but every panel is different. So there's no economy of scale. So what we did after that as a second pass is basically started to look at this as families of identical components. And what we're working here with is basically assemblies of cone geometries, and you know that there is a tangency continuity issue here, where basically you want to be sure that the panel they remain smooth, like on an aircraft skin. And basically, we have to ensure that while we're still getting this curving effect in this direction, we actually want to have as many common panels as we can. So by working with cone geometries, you know that on a cone, the canting angle and the radius can be different. The canting angle has to be the same, the height, top and bottom of the cone segment need to be the same, the radius can change, and they will be still tangent continuous. And what that does is that now we can actually apply this to all 4 towers, and there's basically replicatable components, so we're now dealing with a finite set of families of components that can be mass-produced, right? So I can now achieve a random design, which is completely free-form, with a finite set of components. And this was really important because in the end, we had to then go, these are A0 sheets. Each one of these is of 1 floor of 1 building, so there was something like 500 of these sheets. These were automatically generated through custom computer code that we produced, where each one of these is not projected, but it's actually unfolded and is marked with a family number, so you can go back to the model, here in the model, where is this family piece? And I can still read its coordinates off the sheet. Obviously, everybody's going to work off the digital model, but for contraction purposes, I still need the drawings because they're the ones that get stamped, signed, and get issued. So people get the model, the drawings, they look at the models on sheet, they're really nice, throw them away, and then they just work on the digital model. The second part of this is another form of research. In this case, sure everybody here will feel right at home looking at this stuff, is we spent about, I think a total of like 3 man-years trudging through factories in China, basically looking at every single factory of every cladding contractor, every fabricating subcontractor, what can they do? Because we have this great idea that everything can be custom digitally manufactured today, and you go to the factory and they go, do you say, do you have CNC equipment? Of course, no. They said, let's see it. Here it is. And you realize they have 1 machine. So 57,000 panels times 1 machine is I don't know how many years, so okay, not going to work, right? So actually realize, what are you going to use the machine for? can it cut curves, as you see on the top right? So we're actually doing, you see on the bottom left, we're working with a guy at the machine writing ISO-G code as we inspect the factory, basically taking AutoCAD curves, generating ISO-G code, and watching the machine cut samples. Some machines will make little circles, some machines will cut little straight lines, if you see them, and some of them, which is the best, they use human CNC, where basically they're taking a magic marker and they're scoring. You can see there with the marker, the pen, and then there's guys with a hacksaw, like, this is really, really, really loud, and they're not using any ear protection, as you can see. And this vibrates like crazy, and then to be faster, they have two guys cutting at the same time, so it's out-vibrating each other. It's an unbelievable noise, like crazy stuff. And for the double curve stuff, they say, well, how are you going to turn the double curve panels? And they have this guy, this really big old guy, and he has a big hammer. He says, okay, which one do you want to form? And he takes the panel and starts turning it. And it looks nice. And you're like, oh, you know, oh my God. And we looked at other equipment, things like variable geometry presses, which was later used on another project in Soho, which I'm not going to show you today, but I should have shown you. But in general, it's like, this is really kind of the lowest common denominator. Really working with the guys to figure out what can be made and by who at what cost, and more importantly, rationalizing it so that you can work off available material. So in China, there's two dimensions of 3mm aluminum rolls. One is 1500 mil, and the other one is 1800 mil. Anything else either won't fit in the machine, or you have to custom order, say you have a piece that's 2 meters wide, and you need a 2000 millimeter roll. You won't find any machine that can use it, and if you did, the minimum order, I think, is something like 100 meters of it. Maybe only need 3 pieces, right? So you have to order 100 meters to make 3 pieces, not going to work. So you have to continuously work this out. And so we made mock-ups with, first of all, with Rationalization and then with others. And what you can see is really, we also didn't have to look at how to panelize this, but also looking at the jointing system, because, you know, you didn't want just like big black silicone joints as you find in China, but rather looking at how to really define the detail, and I'll show you a bit about this, so that you get that monolithic continuous curve that you could see in the original model that we made. So that all that information has to get issued digitally as part of the bid tender to 5 different contractors, and they receive all the digital models as basically bid information. And also what they were required to do, which is quite unique, is each contractor that wanted to submit a bid had to make a mock-up. And we set up the mock-ups on the job site, one after the other. You can see they're really huge. And basically, with the client, we looked at not just how well it was performed. So you see this really beautiful curvature continuity from panel to panel. You see there's basically, what in German you call it, Kopfphrase, right? This little drain edge. But we also have this very fine detailed joints. But more importantly, what we are interested in is the development of what we call the common rail system behind, which is basically, if you can CNC form pipes, much like a roller coaster, like an Achterbahn, you know, they're all tangent continuous. I can deliver panels that will then be guaranteed to be tangent continuous based on the subframe that they're being built on. Obviously, every company's got its own interpretation of that, and for those of you who already have a lot of work experience, you know, you have to do a lot of redlining and checking with them. Basically, we built all the details in 3D, working out the models. And what really helped us there, this is to me my favorite image of the whole lecture. This is my colleague Rolando at the time, who is essentially working with the contractor and the client here. And we have a lot of language barriers, as some of you know. But here, the basic digital model allows us to overcome that, because the gray shapes on the right, these guys, they're our model. They're basically our issued external face of glass for the glazing, or external face of material for the sheet metal. And all this other stuff, all these brackets, all the supports, that's coming from the contractor. We're basically overlaying and checking that it actually fits together and implements one common system. Now remember what I told you about Boeing, and remember the images of Boeing, about them bringing together different fabricators into one environment. This is what we're starting to do here. So because they're like paper, these panels get delivered flat to the site, and literally they are flat. They come with the ribs already pre-installed, these lines, which help it curve. This is a piece of the cone, and the cone is so slender you can hardly look at it as a cone. And when you lift it up, it goes and actually starts taking that shape. And all you have to do is anchor it in, and you have your continuous curve panel. And what's really brilliant about this is because these get delivered flat, you can stack many of them together in the truck. They're not very big because they're within this size limitation. And these things just went click, 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 click. got installed. And going back to the story process, what's important here is this image. Because when you drew this in plan, remember now thinking about a client, right? And you're the architect trying to take responsibility for what you're trying to design. If you draw it in plan on this, and this is at the roof of the building, it's curving around, and then the mechanical systems guy in the LDI comes and draws all the ducts, all the different chiller units, and so on. And he put it inside, and it fits inside the slits really well. But then we said, well, look, Mr. Klein, we don't think this is going to work. And we actually showed them, if you put them, place them in space, and you draw the Sliver system, which we had designed around it, look at what you get. And these guys were like, oh my God, you know, this huge light bulb went up and stuff there, and decided that they could not build this with paper alone. And this is obviously the rectified version of what got built. So Stefan was did this one, right, to coordinate that whole roof system. And you could not have done this. Because even if you think it could work, if I take a section, a long section through here, I won't see any clash, but I just forgot to take the section through here. When you get to the job site, if I take the skin out of this stuff, there's so much equipment up there, there's no other space to put stuff. So if you didn't figure this out before, you will never fix it on the job site, and it will just be a disaster of biblical proportions. And that plays itself out again with the structure. So again, framing beams, mechanical system comes in, they're all clashing like crazy, you can see. So they have to be compacted, fit under the framing beams, but above the 2,400 mil clearance of the drop ceiling. So they pass underneath, like here, right? So this is basically such a all detail. We have many, many other examples of such things that we resolve. And a lot of information goes into this. It's a lot of manpower. And you think, why? A lot of people say, why do I have to do all of this? But actually, again, it allows you to have an integrated process where everybody's working together in partnership off a common data set. And that data set gets taken forward and used on the job site in a cyclical environment where we're using lasers to survey locations on the job site, but then we're using things called total stations by light geosystems where we're resurveying what's built and bringing it back to the model, comparing, are we within where we need to be, so that everything else will fit together. And this happens continuously. So there's a real-time, if you like, quality control process that mirrors back to taking the digital environment, digitally built model, and actually executing it in real life. And then, we would also take the computer out, so like, Stichprobe, take it out and basically do some checking on-site bolts coming together and making sure that it works. And as I said, different construction environments. You have guys building scaffolding like this, you have guys dancing around pouring concrete. Very, very fast, very rapid job site. The whole cycle of this building, from starting from the blank sheet of paper to the opening day, was about 3.5 years. For 330,000 square meters and about 60,000 panels. We went from digging the hole in the ground in January. This was already then basically a little less than a year later. And, again, the whole concrete model that gets built. Panels I've already mentioned, but I'm just going to show it to you again, because as they come on, you start getting these bands. You see now, you're never going to stand next to the bands, right? Because it just doesn't exist. You'd have to be flying around the building. But from a human eye level, you can see that they now look like a continuous white band. Some of the contrast you see going up between the batons. But this is really important, right? So now go back. You look at this curve, and I can really kind of that curve. It's a fully rationalized piece of geometry. It's a fully componentized set of families, but I read it like a free-form set of parts. All right, so I'm just going to show you quickly here a few images and carry on. Don't build it next door. My French neighbor in the morning. And we then basically have very, very few parts, which are the bellies, parts of the bellies of these bridges, like the full bubble part, where you actually need to double curve the panel. So we went from basically a 3D model that was 100% double curve to having something like maybe I think 1.5 to 2% double curve panels. Everything else was single curve sheet metal. Atria, and then you see this kind of human, kind of nice landscape that we have. It's a very rare now in Beijing to find this kind of pedestrian space. You find it in Sanlitun and here and a few other places, but mostly it's cars. So having a space like this, you'll see that black line on the right. They haven't closed that yet, but that's a seismic joint for earthquake movement. So that gets a full deformable back panel behind it, so you don't see it. But that's actually where the buildings are moved. So you see a lot of different shapes. but still building families and parks. This is open at night. On opening night, we have 20,000 people turn up all around Zaha. She's sitting here in the middle with a client giving a lecture. I'll just conclude now. I'm just going to quickly show you one more thing, which is another project that the office is working on. And the office has been, which is the stadium in Tokyo, and the office has been working more and more on infrastructural work. And infrastructural work has slightly different concerns than commercial work. Commercial work is really driven by commercial parameters. Infrastructural work is typically driven by parameters of system complexity. In this case, one of the projects is the high-speed train station in Naples, in Italy. This was an early competition we did for a small airport in Zagreb. The reason I'm showing you this is because actually we are working on some very large airport projects right now. Unfortunately, I cannot show you any of them, unless you come to see me later. But basically, that's probably, with a hospital, the most difficult piece of architecture in architecture when it comes to an airport. Because the amount of systems and the amount of, shall we say, repercussions that changing one aspect of the design will have on everything else. On how the aircraft depart, how the baggage systems move, how you distribute baggage, how you distribute people. You can't just say, I want an airport that looks like a star or like a square or whatever. It is really, really driven by many, many functional parameters. It has to do with how you make connections at gates. It has to do with the spacing of runways, and therefore the space you have on a piece of land. An enormous, enormous amount of constraints that you can actually, with a computer, theoretically could solve and actually generate your own airports, because it's a multi-variable constraint system, how you build airports. So it's actually one of the things that I've been working on the most recently are these airport projects, and they are just a different level of complexity and very fun to do. But in terms of sports are very complex as well. The office, as you know, built the Aquatic Center in 2012, and that was led by my colleague Jim Hebron, who's one of the directors in our firm, who was responsible then for taking us through the construction. And one of the things he explained to us was, with these side barriers that were temporary, they, as you know, have now been removed. They now have permanent glazing installed. If you go to London, you can spend £3 British and go swimming. Is that this space was actually driven not even just by the internal spatial beauty, but there are many, many constraints about the internal form to do with camera angles and how you actually visually transmit the images around the world, because the amount of people watching this on TV are going to be many, many, many thousand times the people actually sitting in the space. In the past, through the consulting arm of the Gary Technologies, we worked on this project together with Arabs, which was originally designed by Herzog, but we worked on the geometry together with Arabs to determine how do you actually rationalize and build the geometry in collaboration with that team to produce, again, a kind of a constructive logic that you can modify and allow basically the design process for that to move from the original design model on the left, which has an outbuilder roof and a certain amount of beams, to reduce tonnage and make it wider, remove the roof, and the one on the right. That process moved within a matter of weeks, and that shows you again that the technology in a certain way allows you to do that. It gets mapped to fabrication of components, so there's a hierarchy of componentization in the digital environment that basically maps to the fabrication process and how you track the digital components so that you then put it out and put it together. And so we did a competition, very fast one, in 2012 for the Olympic Stadium in Tokyo, which the office won. It basically replaces the existing stadium. You've probably seen this around in Yoyogi Park. So right now that site is the current stadium, which is the one from the 1964 Olympics, and will now be replaced by this larger stadium for 2020. And one of the things, obviously, that it has is this optical roof that you see in the middle that we can close. The stadium is a very particular design, because one of the things that the team wanted to do is make sure that it's not a stadium that's just hermetically sealed. As you know, there's stadiums that are very beautiful to go to, but if there's no event, it's just like a closed black box. You can't go inside, you can't see inside, you can't use it anyway. It just gets left there like a big artifact. So one of the things that the design team, which is led by my friend Pablo Flores, came up with is these walkways. And the walkways here are basically public walkways that can be used at any time by the public, even when there are no events. As you walk through these walkways, there's restaurants and cafes up here. There's now down here there's a sports museum, and basically you can partake in the space and look inside it and somehow have a dialogue with it on a human scale, even if you are not kind of part of an event and you see the little people that are moving through. It also helps communicate to different parts of town that are potentially separated by this very large building. So the public aspect of this building was very important, as was the aspect of being able, again, what the client here, the Japan Sports Council wanted is a stadium that is reconfigurable so they can do many things. One is, of course, track and field. So when they do the opening ceremony and then all the sports, 100 meters, whoever will be the Usain Bolt in 2010 will be running in there. But at the same time, that you can have movable tiers of seats at the bottom and bring it much tighter, because before the Olympics, they're going to try this on the 2019 Rugby World Cup, which you can see here, and then in future will also be used by the Japan J League football, soccer, to play football. And all of these, as you know, to get a really good soccer football experiences, you have to bring the public as close as possible to the playing field. You can only do that if you have a series of reconfigurable tiers. Another aspect, of course, is having events like Lady Gaga here, or something like that. And you know, in order to control acoustics, one of the issues here, there are operable roofs, you can close it to basically have an acoustic mitigation to the outside world, so actually keep the sound inside and make sure that all the residential areas outside are not kind of bothered by all the people sitting in here. So similar process as I talked before. I tried to write it in German because I thought I was not speaking in German, but basically you have the design architect working with our sports venue designer designing the seating bowl, and then there's basically a joint venture on Japan side, which is basically a series of very large Japanese local architecture firms, mainly which you probably know, like Ceccato, who work together with our Japan to execute the project. So we have this kind of global coordination process between London and Tokyo, and as I mentioned, over the course of the evening, this is something that's repeating itself more and more in the office. And similarly, again, we are now mapping integrated project delivery now with Japanese phases. So we have what you would call what is a design process, what is actually the design being done by the Japanese, and what's actually being built. So we have an initial framework design where we state out what are the parameters of this design project. Will be scheme design, and Jishi sector, which is like design development, and then the actual so-called Koji Country, which is an integrated construction documentation and construction process led by contractors. So you get these very large Japanese companies that are working on this together in Tokyo. So the information has to be organized in a very logical way. We have, again, the information broken down into components, a podium of public art around the stadium, basically with the envelope around it, where people can also go and they have different clubhouses and amenities, coffee shops and so on. The seating bowl and the structure of the plan above. And idea, again, is that we're working off digital information that we're exchanging between multiple platforms, between ourselves in London and the Japanese team in Tokyo, to make sure that that information gets continuously circulated between London and so again, you have basically a design model living in virtual space. It's like an embryonic baby here coming to life. And the building, again, is made up of very large parts. I mentioned it's a structural system, and we have these different membrane groups, one of which is alcohol, and the bowl structure. And basically, they shroud around the actual seating envelope itself. So there's then a consideration of how these things are going to be actually made. And what are the different options for getting them achieved? One of the things, of course, is that there's been a process that we've been doing now of rationalizing the very form of the building. So as I mentioned before, in the process of Galaxy Soho, where we looked at a series of component families, we've been doing here, so we started looking at symmetries and basically having a more compact stadium built out of geometries that are basically coming from the same geometric root source. Within that, we have an optimization going on at the bowl. The bowl needs to be configurable for track and field below, or for something like football or rugby above. And it has to be flexible both by moving these tiers. I can have different solutions to the sports, and they will then give me again, in this case, what we're looking at is quality of view, and the greener it is, the better is the quality of view into the field. So we're looking then at actually the construction process. What are the different force paths? This is something that we're doing again in collaboration with the Japanese. And there's many different ways you can do this. It's a very large span. And so therefore, the pieces themselves, the structure are going to be very large. And they can be made in many different ways. It could be a clad truss system, it could be monocot, which is like the stadium in Beijing, which is basically welded steel plate. Or it could be like an aircraft on the right-hand side, which is a semi-monocot, where we're looking basically at a rib-reinforced kind of shell environment, which is, if you like, how the aircraft. These then have to come together. On one hand, as a complete structural system, but then at the same time incorporate the nuances of the form, and then will then enclose the membrane that surrounds them. And one of the main things, of course, is the design of these biggest arches. And these are something, again, similarly to the project in Beijing, where we're looking at simple geometry to achieve these very complex forms. We don't want to have arches that are made of steel plates that are twisting, but rather are simplified and rationalized to a set of components that can be easily manufactured and controlled in production. So either it's a single arc or it's a combination of multiple arcs. And similar to what I explained in Beijing is the idea that, again, we're working on cones. The cone allows us, because as you know, the curved side of the cone is a flat, developable surface. We know that we can cut these out of sheet metal, like a big steel plates, and weld them together without deformation. And basically, what looks to be a very complex shape is now being actually rebuilt out of very, very simple geometries. Within that, then, development going on with the cable that moves, different membranes. Again, they have different logics applicable to them, and you need to kind of find the membrane to look at what is the sag and the form of this that will give it a certain tensile strength, but also kind of maintain that aesthetic sort of language of this kind of inward curving of these different antiplastic surfaces. And this is something also that Patrick was very interested in maintaining, to make sure that the dynamic shape of this building will be maintained. So developing, if you like, different structural systems for the fixed parts and for the operable parts is a big part of what the team is doing now, to making sure that we can actually achieve that curvature we originally had as a set of operable parts. So that's kind of where this project is now. I'm just going to quickly flick through a couple of images where you get an idea of where we are. We're developing the project further, and hopefully in the end we will have a stadium that everybody can be proud of, and certainly when we look at the Olympics in 2020 will be very interesting. So thank you for listening, and I hope you come back. What's called GT now, yeah. GT. We're using that on the org.
So you use that, which is on. And could you like speculate on that? Because I know that you could basically have an immersive model where the data is on display and then it flashes the information you need to know depending on the profile. We know that I don't know, like there's a big moves in virtual reality and such stuff these days. And I'm wondering where do you see that going? With like scanners on the side to show like your laser on the side.
Yeah, I understand what you're saying. There's this kind of, I don't know, there's like an ideal world, right? Which is what Boeing tries to do. Even from my dealings with them, they have a hard time. But basically, Boeing, we all have to work on one common platform, one set of technologies with approved protocols that nobody can work with anyway. Our industry is, of course, much more diversified than that. And the main way that you can control that is to convince your client that that's going to be the better way to control the project, right? And that we do that from the design instance right through the construction process, like I showed you the example in Beijing. So we're striving, if you like, to achieve an ideal. where we have the most control we can have of the process that gives us the confidence, as I said, reduces risk. But from project to project it's different. Some projects it'll happen on certain parts, and some projects it grows. So in Beijing, kind of knew we were going to do most of it. In New York, it's an evolution, right? We've done enough for the cladding. We might, we're now going to get more MVP data for the clients, but also the executive architect is taking over, so we have to make sure that they continue the process. And so it depends what kind of project you're working on, what's at stake, and ultimately what is the big picture of this. I mean, I've had conversation already with people that we're doing airport work with the client, even though we don't even have a design yet. They know that they want to do this because it's such an enormous project. We're talking about buildings that are, really, really big, and as I said, really complex. So it's a question of the kind of trades you also bring on board. So will the contractors be able to make use of any of this data? Will it be meaningless? We found typically that the cladding construction companies are the ones that are the most advanced in using this kind of technology. So it really is just a way for us to ensure that we maintain the necessary control level and therefore feel comfortable that the project will get built as we designed it. Sir?
You have shown us a lot of processes where there is a lot of optimization of the shape, optimization of how to build something. And if you go too further into optimization, then you say, okay, we want to have less pieces, and that may take you to some kind of symmetry, where if you build one side, you can replicate the other side, and it is cheaper. And they can also take you to a two-axis symmetry, which is much cheaper.
Absolutely.
The question comes that, do you think these processes will drive more and more the design architecture that you're looking for? Because if we look at the ancient times, they would say, okay, we will build the pyramid, we build one type of block, and then that will be cheaper, and then we will make a lot of them, and so on. Is it that, are you afraid of this happening on the work?
I think it's an excellent question. And so the short answer is, I really hope so, right? And I think that's certainly like what I think the potential of the technology really is to not that we come in and kind of like Mr. Fix-It, we have this, somebody designed something to make it work, but rather say, how do you actually design with that in mind? So other offices do that to some extent. Foster works according to what they call first principles. But I think actually technology allows them to go beyond that. So if you look at some of go back to kind of more academic research on this, some of the stuff you describe is what would get referred to as post-rationalization, where some projects might be, quote, pre-rationalized, where you only pre-rationalize like you're working with Lego, right? These are the pieces, what can they do? What we found is that you can actually use the technology to go through, again, say, the parametric authority data, where the parametrics ensures the way. By parametric, I don't mean it in reconfigurable shapes, like other people might use the word parametric. I mean really about variable geometry components. And that you would refer to as co-rationalization. So basically, it's embedded in the technology you're using, and it's embedded in the process of design with these tools, that you know that whatever I can do within this space, it can be manufactured within certain limits. And there's some very good software tools that allow you to do that, and will even tell you if you're exceeding certain things, like I told you, for example, a simple one, like the width of the coil of aluminium. Whatever I do cannot be bigger than that because it won't fit or any bigger coil. So if I can have a tool that helps me define the playing field and helps me control it, then it can be a much, much more intelligent design process. That's one thing. The other one is, when you talk about, you mentioned the word optimization. And again, optimization is just trying to get as many common parts as I can. But actually what we're also talking about is, can that optimization happen in a search space, right? So if you think about, there's a lot of interesting things like evolutionary design and rule-based systems, and can I actually use things like search algorithms based on genetics, like genetic algorithms to find solutions. Again, can you do that as a proactive measure to basically produce an optimal form? And some of the work that the research guys in the office are starting to do is going in that direction. Is instead of coming up with one solution, come up with a framework. And the framework then steered by different criteria, which might change project to project, which might be cost, size, whatever. Then that system helps you come up with a really good available solution. So I think we talk about it a lot in academia, but in practice, there's a long way to go. So lots to do there. Any other questions? Anyway, I hope, yes, sir.
If you think about what you said about facade consultant like Xander are starting to give up but like display their tools on the cloud, like give their parametric tools and give elasticity with the cost relation to have it. This is a really different take on that. I'm just wondering if this is a possibility in such a parametric-based design project. Okay,
so you're talking about embedding intelligence within the tool so that somebody else can use it.
I'm talking about the architecture actually being releasing its parametric tool to see what happens within a class.
So that's a very interesting idea. That's been explored in the past. Basically, I had a teacher when I was at the IoA doing my diploma there. There's a man called John Fraser who was one of the godfathers of really using rule-based computation, not just kind of shaping, but really the logic behind it. And his idea was that if an architect could codify kind of digital code, much the way we have a DNA, the information of their building designs or their design approach, that anybody could replicate building even after that architect was gone. And he showed that by building a kind of a robotic system that had that from an architect who passed away in the UK. Well, and basically this thing would crank out component-based houses by this guy. Another friend of mine, who's now a professor in Lisbon, he was overstudying at MIT, a guy called Giuseppe Duarte. And he did his thesis on a series of villas that were designed by Caesar, by Alvaro Caesar. And what he did was that these villas were based on common typology that Caesar had developed. But they were all a little different. So he actually worked with he was doing his PhD, and he produced a system on the computer that would crank out shape grammars, codifying the shape grammars to produce other versions of Caesar. And they went to Caesar, and they showed him the project, and it was like a placebo test, right? They showed him his stuff and the other stuff, and he couldn't tell them apart. He couldn't figure out which one was his and which ones were the ones done by the computer because the rule set was so clear. So, I mean, even at that nuanced level, you couldn't theory codify it. The question is, why would you do it? So, would you do it because you're trying to sell an idea with it? Are you doing it so that somebody else can make use of it in a different way? I would be interested to know what the motive behind it is, but I think you can probably do it if you have a very clear set of rules. There's another person called Michelle Kaufman, who's in San Francisco, who used to work at Gary's, and she set up a company that produced pre-manufactured houses, but you can choose the components, and each house looks different, but they're from a common set of kit parts, right? So you can say it's a Michelle Kaufman house, but it's a very individual house. I know you guys are going. Go ahead. Go ahead.
I was just wondering, you were talking about the design, the timing of the project and the design part being able to being squashed together, but not the construction side. And I was wondering if those BIM technologies are also influencing the contractor side, or is it becoming a contractor's regime that they're kind of putting their parameters into our models and then kind of dictating the way architecture goes?
It's a good question. So, for example, if you go to a contractor like Lane Work, which is a very big contractor that works in the UK, they work in Hong Kong and Australia, so on, worldwide. They have a team called the Engineering Excellence Group. The Engineering Excellence Group is a team of, I think, there are like 50 or 100 people, who looks at how to do exactly that. So they're looking at how to preemptively work with the design team so that early on, the information of fabrication, without limiting the creativity, but if you're working on a large project, how can you bring that information in early to help guide the design process? So that, again, when it goes towards the construction side, the contractors will go, oh my God, I don't understand this. Or it's very difficult, so they're going to have to price risk into it. So they're going to have a risk contingency, right? So they're going to have 15, 18, 20% to a contract and say, you know, I need to have something to protect myself because I don't know how to build these curved metal panels because I've never done this before. So I think it's going to be that much. That's how much of the material costs. But there's a difficulty there, and there's a risk I have to manage. So you can lower the risk, and therefore lower the actual cost of construction. So if you can use this information early on to better understand the design in its infancy, so that really when you're sitting with the design teams and you're working through this, you have the chance to, if you like, be confident that you kind of know downstream. A little bit you know from just the firm has a lot of experience, and you know in-house collectively we have a lot of people who know many things. But to put together in a way that the client says, I kind of get what you're trying to do and we know what the issues are going to be, and so that we can bring this forward with the contractor, that certainly starts to play a really important role. So if anything, we welcome the idea of contractors coming on board early, we welcome the idea of collaborating. Zaner before, people like that, who bring you knowledge about how stuff might be made. Because the difference between working also with consultants, we work with many great consultants, but when you work with a fabricator on a cladding system or a large contractor, they know what they really can do and what they can really build. So what the consultant does, it consults to the architect to produce the documentation information as best it can to help the contractor understand what you're doing. But if you're bringing in knowledge that's coming from the contractor's own experience, the value of that information goes way, way, way up. And you can do that without actually literally giving the contractor control and design for you. That's not the exercise. It's just how can you best inform the process.
Any more?
I know you guys are doing this moment and you're all really, really busy. And I really, having done this myself, I really appreciate, like, I don't know if I would have gone to my own lecture all those years ago because if you're working on your diploma, it's really important that you get that done, and I know many of you guys have.
You are confronted with the helpers.
Oh, the helpers. Oh, okay. Okay. Well, thank you, helpers. please give the executive summary to whoever's in your diploma.